Assalamu alaikum. Welcome, dear students, to our fourth part in Chapter 17 in Newton's laws. In this video, we will apply on Newton's first and second law by solving a typical exercise. But before we start, let's have a quick recall for some previous objectives. Newton's first law states that when an object is subjected to several forces of zero resultant, it remains at rest if it was initially at rest, or in uniform rectilinear motion if it was initially in motion. In other words, the sum of the external forces is equal to zero vector and the velocity vector remains constant. Newton's second law states that the resultant of the external forces acting on an object is equal to the product of the mass of the object by its acceleration vector. Now we need to go back to the time equations of motion for the different types of rectilinear motion. Remember that in a uniform rectilinear motion, x is equal to vt plus x0, where d is equal to the absolute value of x minus x0, which is equal to vt. The acceleration in such type of motion is equal to 0. And if the direction of motion is with the chosen positive sense, then the velocity vector is positive. Now let's move to the other types of rectilinear motion, which are the uniformly varied rectilinear motion. In such types of motion, v equal at plus v0, x equal half at square plus v0t plus x0, and the distance traveled is equal to the absolute value of x minus x0, which is equal to the absolute value of half at square plus v0t. And the equation independent of time for such type of motion is v final square minus v initial square is equal to 2ad. And don't forget that for a uniformly accelerated rectilinear motion, a dot v should be positive, which means that a and v should have the same direction. Whereas in a uniformly decelerated rectilinear motion, a dot v is negative, then a and v have opposite directions. Now let's practice by solving the following typical exercise. A car of mass m equal 1000 kg starts from rest and moves along a straight path. During its motion, the car passes by three different phases. The force of friction is assumed to be constant over the path of magnitude of r equal to 100 Newton. Let's start with the first phase between the interval t0 t1. At t0 equal to 0, the driver starts moving from rest with a constant acceleration a1 equal 2 meters per second square under the action of the motive force F1. In the first part, you are asked to represent, not to scale, the forces acting on the car and consider the car as a particle confounded to its center of gravity. Actually, the external forces acting on the car are the weight of the car applied in its center of gravity vertically downward, the normal reaction of a support N, we apply it or we represent it also from the center of gravity vertically upward. We have the motive force F1 vector, which is directed to the right along a horizontal line, and also we have the force of friction of r vector, which opposes the direction of motion, so it is directed to the left. Now we are asked to apply Newton's second law to calculate the magnitude of the motive force F1. By applying Newton's second law, which tells us that the sum of the external forces acting on the object is equal to ma vector, the external forces are w vector plus n vector plus f1 vector plus fr vector is equal to ma1 vector. Here we need to project along the axis oriented positively in the direction of motion, which is the x-axis in our case, and here is the axis. Upon projecting or after projecting, we obtain that f1, which is positive since it is with the direction of the axis, minus fr, since the minus corresponds to the direction of r, which is opposite to the direction of the axis, is equal to ma1. Then f1 is equal to fr plus ma1. We substitute each factor by its value. Fr is equal to 200, m is equal to 1000, and a1 is equal to 2. Upon calculating, we obtain 2200 Newton. Now we are asked to calculate the speed of the car v1 at the instant t1 equal 10 seconds. Actually, the car moves in a uniformly accelerated rectilinear motion. Then, from the previous equations we have recalled after a while, v1 is equal to a1 t1 plus v0. But v0 equal to 0 meters per second since the car starts moving from rest. Then we replace A1 and T1 by their values and we obtain 20 meters per second. Then at the instant T1, the velocity of the car or the speed of the car is V1 equal to 20 meters per second. In the fourth and last part in this phase, you are asked to calculate the distance D1 traveled by the car during this phase. Actually, you have two different methods to calculate the value of D1. Starting by the first method, D1 is equal to the absolute value of half A1 delta T1 square plus V0 delta T1, where V0 is equal to 0 meter per second, delta T1 is equal to 10 seconds, and A1 is equal to 2 meter per second square. We replace these values in the equation to obtain 100 meter. Or the second method is to use the equation independent of time, which tells us that V final square minus V0 square is equal to 2AD. Actually, V final of this phase is V1, and V1 is equal to 20 meter per second. The other factors we have them, so we substitute, and D1 is equal to V1 square minus V0 square divided by 2A1. By replacing the factors by their values, we obtain also the same value, which is 100 meter. Then in this phase, the car covers 100 meter in 10 seconds. Now let's move to the second phase between the instants T1 and T2. At T1 equal 10 seconds, the driver reduces the magnitude of the motive force to become F2, so that the car moves with a constant speed V2 equal 20 meter per second, where the car covers a distance of 100 meter during delta T2. This is F2, the motive force applied by the driver, so that he moves with a constant speed. In the first part in this phase, you are told that the motion of the car verifies Newton's first law, and you need to justify why. Actually, since the speed of the car is constant along a rectilinear path, then the acceleration vector in this case is equal to 0 vector, which means that the sum of the external forces acting on the car is equal to 0 vector, which verifies Newton's first law. Or we can simply say, since the car moves in a uniform rectilinear motion because its speed remains constant along a straight trajectory, then the sum of the external forces is equal to 0 vector, and this verifies Newton's first law. In the second part, we are asked to deduce the intensity of the motive force F2 in this phase. We apply Newton's first law, where the sum of the external forces is equal to 0 vector. The external forces are W vector, N vector, F2 vector, and Fr vector. Their sum as vector is equal to 0 vectors. Now we need to project along the same horizontal axis mentioned in the previous slides. Then we obtain F2 minus Fr is equal to 0. This implies that the magnitude of F2 is equal to the magnitude of Fr, which is equal to 200 Newton. In the third part, we are asked to calculate the duration of time delta 2 of this phase. Don't forget that in this phase, the car moves in a uniform rectilinear motion. Then the time equation we can use is t equal v times delta t. Then d2 is equal to v2 times delta t2. Then delta 2 is equal to d2, which is equal to 100 meter, divided by the constant speed, which is 20 meter per second. And this implies that the duration of time of this phase is equal to 5 seconds. Now let's move to the third and last phase, which is between the instants T2 and T3. At T2, the driver notices that the red light of the traffic sign is turned on, so he applies the brakes to stop the car. The force of brake applied to the car is assumed to be constant of magnitude Fb equal 500 Newton. Note that the driver in this case takes his feet completely off the accelerator pedal, so there is no motive force anymore, where the only forces acting on the car in this case are the weight, the normal reaction, the force of friction, and the force of a brake applied on the car. Now in the first part, we are asked to determine the acceleration A3 of the car, then deduce the nature of motion of the car in this phase. We need here to apply Newton's second law, which tells us that the sum of the external forces acting on the car is equal to ma vector. Then W vector plus N vector plus Fb vector plus Fr vector is equal to ma3 vector. Also, we need to project along the same axis we have mentioned before, which is the x-axis. Then we obtain minus FB minus FR is equal to MA3, and the minus corresponds to the direction of the forces FB and FR compared to the positive direction of the axis. Then A3 is equal to minus FB minus FR divided by M. After replacing each factor by its value, we obtain that A3 is equal to minus 0.7 meter per second square. Now to move to the nature of the car, since the trajectory is a straight line, the acceleration is negative and constant, and V is positive since the car is moving in the positive sense, then A3 dot V is negative, which means that the motion is uniformly decelerated rectilinear motion. Now you are asked to deduce the duration delta T3 needed by the car to stop. Since the motion is uniformly decelerated rectilinear motion, then we can use the time equation V3 is equal to A3 delta T3 plus V2. Don't forget that V is the speed at the considered instant, and V2 is the initial instant of this interval, the speed at the instant T2. Where the initial speed of this interval is 20 meters per second, the final speed is 0 meters per second since the car will stop, and the acceleration in this interval is equal to minus 0.7 meters per second square. We replace these values to obtain that delta T3 is equal to 28.57 seconds. In the last part related to this phase, you are asked to calculate the distance D3 traveled by the car during this phase. Also, since the car moves in a uniformly decelerated rectilinear motion, we can use the equation independent of time, which tells us that V final square of this phase, which is V3 square, minus the initial speed of this phase, which is V2 square, is equal to 2A3D3. We replace each factor by its value to obtain that D3 is equal to 0 minus 20 square divided by 2 times minus 0.7, and this gives us that the distance traveled in this phase is equal to 285.7 meters. Now finally we are asked to determine the average speed of the car during its entire motion. The average speed is calculated by dividing the total distance traveled in the entire motion by the total duration of time. In the first phase, the car covers 100 meters in 10 seconds. In the second phase, the car covers 100 meters in 5 seconds. And in the third phase, the car covers 285.7 meters in 28.57 seconds. Now we can start replacing. The total distance is equal to D1 plus D2 plus D3, and the total duration of time is equal to delta T1 plus delta T2 plus delta T3. We replace all these factors by their values, and finally we obtain that the average speed in the entire motion is equal to 11.14 meters per second. That's for today. I hope this exercise will help you solve Newton's laws problems. Thank you for your attention, and goodbye. See you in our next video.